What is up, guys? It's Adam back with another video, here to give you an introduction for the new Keras course that I'm doing. This course will take you from basic Python knowledge to being able to create your own unique deep learning applications in just a couple short videos. The easiest way to learn is by doing. So in this course, we will be building 4 different deep learning and machine learning applications. The first one is a linear regression model, which we are going to use to predict housing prices based on square feet. And the second algorithm that we'll be using, which is a deep neural network or an artificial neural network, we will be using the same data set but expanding it so that we can more accurately predict housing prices based on square footage, location, and a couple other variables. The third algorithm that we'll be using is called a convolutional neural network, which we will use to be able to predict handwritten digits. And finally, the fourth application that we'll be building in this course is a recurrent neural network, which we will use to make an AI that can generate fake text in the style of a particular author. When I was learning machine learning, I got really confused with a lot of the jargon and math behind the algorithms. That's why I created this course. If you want to get up and running with deep learning applications as fast as possible, this course is for you. So with that being said, what are you waiting for? Let's get started. Alright guys, so today we are going to be discussing linear regression, which is the most simple machine learning model that I could think of personally. It's also one of the most useful machine learning models because it requires very little processing power and can be applied in a wide variety of applications. So those of you who have taken statistics, you may be familiar with this model. In that case, you can just skip this video and we will get to the coding. So in short, linear regression is a way to tell the relationship between an x and a y variable. So what we're going to have is we're going to have a bunch of data points on the x and y axis, and what linear regression is going to try to do is find a linear line, a linear relationship between the x and y values. So then we can predict other x and y values that aren't actually plotted. So what does this look like exactly? Well, it looks like this. So right here, the green squares that you see, those represent the different data points and they're plotted on the x and y plane. And what linear regression is trying to do is it's trying to make a straight line. It's trying to make a straight line that minimizes the error. Now the error right here is represented by this red line right here. What you see it is it's y hat, meaning the predicted y value, which is the line right here, minus y, which is the actual y value, and then that's in absolute value bars. So what this line is doing is it's slowly adjusting itself to find the correct slope and the correct intercept. So we have w naught is the intercept. It's trying to find the correct slope and the correct intercept that makes the total error as small as possible. That makes it so that each of these red lines are as short as possible and that the line is as most representative of the data as possible. So once it creates this, what it's going to do is now you can predict values. So for instance, we can say in our example that the y right here, this represents the sales price of a house, and the x right here represents the square footage. So here are all of the houses plotted with their square footage and their sales price, and you can see the house with the biggest square footage also has the biggest sale price, and the house with the smallest square footage has almost the smallest sale price. So from there, when it creates the line, what you can do is you can predict. You can say, okay, well, if there's a house right here with this amount of square footage, we can predict about what the sale price should be. So that is what's useful about linear regression, is that you can make simple predictions like that. And you can apply it to literally any linear relationship you can think of. I'm just using the example of housing prices because that's what we're going to be working on in the next video. So the math behind this equation is actually quite simple. It does look a little bit intimidating, but all you're really right here trying to get is you're trying to optimize for the population y-intercept, the population slope coefficient, and then the internet independent variable with the error. And you're trying to minimize the error as much as possible so that it makes the line of best fit. Now with that being said, sometimes you can have your model overfit or underfit. And this is something that applies to most, pretty much all algorithms have a problem with overfitting or underfitting when you're running your models. So this is good to keep in mind for the rest of the course and also when you're doing machine learning on your own.
In fact, overfitting is such a common problem that Udacity did a parody of Michael Jackson's Thriller about it.
You overfit it, spit it out. Mistakes you shouldn't make, evaluate the testing set. You overfit it, quit it now. You'll need another way or you'll regret it. Get it, no doubt.
So an example of an underfitted model would be right here. So here we have the X and Y data, and you can see this linear relationship. You can kind of see where the model's getting that from, but it doesn't accurately describe the data because you have stuff over here, stuff over here, stuff over here. Now a good fit for this data would be something like this. So this isn't linear, this is logistic regression, but you can see it fits the data much better. So underfitting's here, and then overfitting is when the model is too good. When it is so accurate at predicting that what ends up happening is it doesn't actually truly describe the data. So this can become a problem because even though on the training data this works perfectly, on outside data, on new data, this model isn't going to work as well as the good fit model right here. So that's why you want to avoid overfitting or underfitting your model, because what can end up happening is that when your model gets new data, then there are going to be some issues. Basically, in order to find out if your model is overfitting or underfitting, you have to look at the loss. And the loss is something that Keras is going to print out for you while you're training. Basically what it is the punishment that the neural network or the model receives for getting something wrong. So if the loss is very, very low, that means that the model is very, very accurate on the training data. And this is actually bad. You don't want your loss to be too low, because if your loss is too low, then it's going to look like the overfitted example right here where it perfectly matches the data but doesn't actually match the data as a whole when you're put into account new data. Alright guys, so by now you all know about linear regression and a little bit how it works. Now in this video what we're going to be doing is we're going to be performing linear regression on some data that I have. And this data is from the Iowa housing prices market, and this is real data. I edited it a little bit so that it could be simpler for our purposes for beginners. Basically what we're going to do is we're going to make a model that'll predict, based on the square feet, what the price of the house is going to be. So we have 1,460 entries of this data that we are going to be training on, and we're going to make a model that's going to be able to predict, based on square feet, the sales price of a house. And this is real data too, which is really cool. So in order to do that, the first thing that we're going to do is import our necessary libraries. So we're going to import Keras, which is going to be our machine learning library. We're going to import NumPy as NP. This is going to do some math for us later. We're also going to import pandas as PD. This is going to help us read in our data. And then we're finally going to import matplotlib.pyplot as PLT, and this is going to let us graph our linear regression model and see what our data looks like, which is really cool. So we're going to shift enter to run that cell and create a new cell. Next, what we need to do is we need to mount our drive so that we can get access to the data. Again, like I said before, you can get access to the data by going on my GitHub and then getting the link directly, or you can download it, save it to your own drive, and do it like the way that I'm about to do it now. Or you can upload it to your runtime right here on the side. The choice is really up to you, but for this example, I'm going to mount the drive, and I'm going to run this. It looks like my drive is already mounted, so all I have to do now is just put in the CSV to our file. So we're going to say df for data frame is going to equal to pd, which is pandas.read CSV. And by the way, if you don't know, CSV stands for comma separated file. So it's basically like an Excel spreadsheet if you think of it. We're going to do the location of the file, which I will get right here by saying copy path. Then I'll paste it into here. I can get rid of the content part. It'll work just the same. And we'll run that. And it looks like our CSV was imported to the file just fine. So that's good. Next, what we need to do is we need to set the X and the Y variables. So if I open up our housing prices CSV again, you'll see the X right here is going to be the square feet, this column right here, and the Y is going to be the sales price, this column right here. So we're going to say square feet is equal to df, which is what we set up here. We're going to do double square brackets and then square feet, which is the name of the column right here. And we're going to say dot values, and then we're going to do the same thing for sale price. So sale price is going to be equal to df double square brackets sale price dot values. All right, sweet. So we'll run that sucker, and now it's time to actually build the model. So the first thing that we're going to do is create the model by setting model equal to Keras dot sequential, showing that we're building a sequential model. And then we're going to add just one layer to the model. So model dot add. We're going to add from Keras dot layers dot dense, and you can learn more about what a dense layer is in the Keras documentation. But basically, we're going to build the simplest model possible in Keras for linear regression. So now a really cool thing about Colab, or also Jupyter Notebook has this too, is that if you press the tab key, what it'll do is it'll pull up a little box right here that'll show you the documentation. So for instance, if you forget all the parameters that need to go into a function that you're using, for example, you can easily just pull this up and then it'll show you everything that you need to know. So from reading this, we can see that our dense needs 1, because we're just doing 1 neuron, and we need it to have an input shape equal to 1 comma, and nothing goes in here, because again, what we're doing is we're feeding in one value and then it's giving us one value back. Okay, so we have the model created. Now we need to compile the model. So model.compile, and we're going to use optimizers. Now the optimizer is going to be that algorithm, that little function that's going to minimize the loss of the function. It's going to minimize the error. So if you think back to last video where we had the red lines, that's basically what we're going to be doing, is we're going to be inputting the correct algorithm that's going to minimize the amount of red lines that are shown on the graph. So we're going to do keras.optimizers.atom, and basically atom is generally considered to be the best optimizer, or one of the best optimizers. Most of them are going to work pretty similarly in this example, just because we have such a simple network and such a small amount of training data, but atom generally works the fastest and the most accurate. And then inside of the parentheses here, we're going to set the learning rate, which is LR, and we're going to have that equal to 1. Now basically what the learning rate is going to say is it's going to say how fast are we going through, are we going to try to optimize, basically how big are the jumps going to be when we're adjusting our model. And so a really small learning rate where it's going like this is going to take a longer to reach the optimum the optimum line, whereas a big learning rate is going to jump down, and potentially you could get it way off, but it will hit it faster most of the time. It'll just be a little bit less accurate. Because we don't have a lot of data, I chose a larger learning rate. Usually you want the learning rate to be much, much smaller. But anyways, and then finally we're going to do mean squared error. And basically what this means is that the error that we're calculating isn't just the error where it's y hat, the predicted y, minus what the actual y is. What it's actually going to be is it's going to be that squared. So there aren't going to be any absolute value bars if you think back to the picture that we had in the last video, and feel free to go back if you don't remember, but it's going to square it, so instead it's going to be like a red box that is going to be trying to optimize for. So any error is going to be squared, not just doubled, but squared, and then the atom optimizer is going to try to minimize that as much as possible. Hopefully that makes sense. If that doesn't make sense, this is kind of my first time explaining this. Please leave a comment down below and then I'll try to edit this video later. So finally, well, let me close out of our data. Finally, what we're going to do is we're going to fit the model, which is basically training the model. So model.fit, we need to fit, if you open up the documentation here, the x, which is square feet. We're going to fit it to the y, which is sale price. And then also we need to count the number of epochs. So that's epoch. So epochs is going to equal to 30. Now basically what an epoch is it's how many times you're going to run through the data. So once the neural network runs through every single data point, which is about 1460 I believe, what it's going to do is it's going to run over that same data again and keep on optimizing, and it's going to do that 30 times. So generally, the larger your data set is, the less amount of epochs that you want to have. But since our data set is relatively small, and because we don't have to worry too much about computational power because we're on a cloud GPU and our model's pretty basic, we're going to have a higher number of epochs, which is 30. So it's going to run through the data 30 times instead of just one time. And then finally we'll have the batch size, which is how many data points are going into the network at a time. And if this is too high, what can happen sometimes is that the model will crash. So we want to make sure that this is a little bit lower, so 10 is fine for our purposes. I find generally that the batch size doesn't matter too much in terms of the efficiency of the model. Okay, so we have the model created. Now it's time to train it by running Shift-Enter. And you'll see right here, we can see the loss that it's calculating right here. And we've gone through all 30 epochs relatively quickly. So now what we got to do is we got to plot our results and see how well the model did. So we're going to do df.plot, and remember df is our data set, and we imported matplotlib as PLT right there. So df.plot. Alright, so the kind of plot is going to be a scatter plot. The x is going to be equal to the square feet. The y is going to be equal to the sale price. And we'll just make a title for it. So the title will be equal to housing prices and square footage of Iowa homes. And you don't have to include a title if you don't want to. It's just generally if you want to save this to a PNG or screenshot it or whatever, you might want the graph to look a little bit nice to show off your findings. Okay, and now y underscore pred, we're going to set that equal to the line, the linear regression line that we just created by training the model. So this is going to be equal to model.predict the square feet. So again, what this is doing is it's saying, okay, so the model is going to predict the square feet that is actually in our data set and then it's going to plot that. And so that's what ypred is. It's basically the y hat value, if you think back to that picture when we talked about linear regression. And then all we have to do now is just plot this. So we're going to do plt.plot. We're going to plot square feet as the x. Y pred is going to be the y, the predicted y value. And the color of it is going to be red so that we can see it. Because default is going to be blue and you're not going to be able to see it very well. So we'll run that. And you see right here, this red line is the regression line that we trained. And then these are all of the different data point values. So it seems to be fitting the data pretty well. However, there is a lot of variance in the data. Now, if we want to predict a new data set, what we're going to do is create a new variable. So I'll just say new SF for square footage. And let's set it, let's say, equal to 2,000 square feet, which is pretty large. And then what we're going to do is we're going to print model.predict, and then inside of here, inside brackets, new SF. And you'll see, based on the model, the predicted price for a home that is 2,000 square feet is going to be $239,000 to buy. So that's pretty much it, guys. You just successfully created your first machine learning model. Let me know if you guys use this linear regression for anything else other than Iowa homes, and I will see you in the next video. Sweet. Okay guys, so in the last video we built a linear regression model and it worked okay. There's just one problem, and that is that housing prices are not 100% determined on the square footage. So because of that, there are definitely a lot of cases in which our model would not be accurate at all. For instance, you could have a very large house that doesn't have indoor plumbing, and so that would make it a lot less expensive. Or you could have a really, really nice house with a smaller square footage that would be more expensive, or maybe it's in a good area. So to account for this, what we are going to do is we are going to build a deep neural network. Not just one neuron, but a whole neural network, and we're going to use that to predict housing prices. So we're going to predict housing prices based on several different factors. And for this, I have a data set. It's an actual data set of real housing prices. It's actually the same as the last one, except for I added some of the features in that I deleted for the linear regression model. Because remember, with linear regression, we were just using two values, the x, which was the square footage, and the y, which was the housing price. So we're going to get started with this. So first thing we need to do is to import our dependencies. So we're going to import Keras. We're going to import numpy as np. And we're going to import pandas as pd. Alright, next what we're going to do is we are going to get our CSV into our notebook. And so in order to do that, I'm going to say df is going to equal to pd.read CSV. And obviously you can import the data however you want. I'm just getting it from Drive because it's already there. And then I'm going to take housingprices.csv, copy that path, and then I'm going to paste it into there. Go to the content. And also, just to show you a little bit what our data looks like, and this will help us later, I'm going to do df.head. So head is a very useful function. Basically what it's going to do is it's going to print out like the first 5 values of the data set so that you'll be able to see sort of what your data looks like. So we'll print that out, and you'll see instead of just having square footage and then sales price, we have the year built, the second floor square footage, the greater living area, full bath, half bath, bedrooms above ground, total rooms above ground, years sold, and the sales price. So because we have more variables, we'll be able to get a lot more specific in our model's predictions. Alright, so next what we want to do is we want to set the x and the y values. So the x value, if you remember last time, was equal to the square footage. However, this time the x value is actually going to be set to multiple values. It's going to be set to all of these values except for the sales price. So in order to do that, what we're going to do is we're going to say x is equal to df dot drop, and columns is going to equal to the sale price column. So basically x is equal to all of the columns except for the sale price column. And then our y value will be equal to, just like in the last video, to the sale price column. Alright, so we'll run that. Everything looks good. Next, it's time to build the model. So if you remember last time, we're going to build the sequential model. So model is going to equal to keras.sequential. Next up, we're going to add 3 layers of neurons. So the first layer is going to be model.add keras.layers.dense, because it's a dense neural network. The number of neurons in this layer is going to be 8. Now, in choosing the correct number of neurons per layer, generally you just kind of have to experiment. There is no exact science to getting this. That's part of the art of data science, is being able to experiment a little bit with the different values. You know, you remember in the last video, like the learning rate and the batch size. It's the same thing too with neurons. So generally what people do is they will assign neurons to the number of attributes they are, in hopes that the neural network will kind of see a pattern there and pick up on it and be able to be more accurate. Also, a good thing to note, the more layers you have and the more neurons you have, the slower your network's going to train. So that's another thing to note. But yeah, so keras.add dense will have 8 neurons. Our activation function will be ReLU, for rectified linear units. Basically what this is saying is this takes all the values and then it normalizes them on a scale of 0 to 1. And the algorithm that does this best is called ReLU, where basically it's just saying if it's closer to 1, then it's 1. If it's closer to 0, it's 0. And this has been found to work the best overall. That's all you really need to know about ReLU. You've also probably might have heard of sigmoid or tanh, stuff like that. But ReLU is generally considered to be the best in most cases, including this case. And then, since this is our input layer, the input shape is going to be equal to, again, 8, which is the number of columns here. Well, I should say number of columns except for sales price. That's what I should say. Yeah. Okay, so next, right here, model.add, we're going to add a second layer, and it's basically going to do the same thing. So keras.layers.dense, it's going to be size 8. The activation function will again be ReLU, and the input, no input shape this time, because this is in the input layer. Okay, and then finally, our last layer will be model.add keras.layers.dense, and this will be a size of 1, because remember, we're just outputting one single value, and that is the sales price. So that's why there's only one neuron there. Finally, let's compile the model. So model.compile. Let me pull up the tab to see what we need. Okay, we need our optimizer. So the optimizer will be Atom, because it's generally considered to work the best. And for loss, we're going to have mean squared error, just like in the last video. Okay, so let's run that. Don't have any errors, that's good. Okay, next up we need to fit the model. So model.fit, so that we can start training. We're going to put in x and y. And then we're going to say the epochs are going to be equal to 30 again, so we're going to go over the data 30 times. And then, so another thing that I want to show you guys is that, remember when I said before about overfitting, how sometimes the loss gets too small, or like the loss is getting smaller and smaller slowly, but then it gets small really fast, and that's usually a sign of overfitting. So to stop that, what we're going to do is we're going to use something called early stopping. So we're going to set callbacks equal to Keras dot callbacks dot early stopping, and we'll give it a patience of 5, which is another thing that you can experiment with. So basically what this is going to do is the model is going to be training, and then once it gets to a point where it's not getting much better, it's going to stop it even if we still have some epochs left. So this will save you some time and some CPU space. Alright, so that looks like it's about it. So, oh, excuse me, early stopping patience is going to be equal to 5. There we go. Okay, so we'll run that. So it's going through the epochs, epochs, and it looks like it made it to 30 without early stopping. And it did it pretty fast too. We got that down. Now let's test out our model. So we're going to test out our model on some test data. And the test data I'm going to equal to a NumPy array, so np.array. And what I'm going to equal it to is I'm going to equal it to this first column right here. So we know what the value of this house is, but we're going to see what the model thinks the value of this house is. So I'll do that. Make sure that there are commas there. Okay, good. And now we're going to run this test data in the model. So we're going to print model.predict, and we're going to say test data, and we're going to have to reshape it because right now it's in a column instead of a row, I believe. So we're going to reshape it to 1.8, and the batch size is going to be equal to 1 because there's only one batch. So we'll print this out. Oopsie daisies. Looks like we forgot a value there. Oh, I accidentally put in the sale price of the house, which is not what we want. We want to predict the sales price. So we'll see here it says that the estimated price of this house is about $204,000. Now if we go up to the top, you can see it's actually $208,000. So we were only about $4,000 off for the house, which is pretty good given the fact that we only had 1,400 samples and how quick this model trained as well. So next, let's say that you really like this model and you want to save this model, deploy it to the cloud, use it for later. I know right now as a beginner this might not seem like something that you might want necessarily, but in the future it will definitely help you a lot. So in order to save your model, what you're going to do is you're going to say model.save, and then we're going to in here put what we want the model to be saved as. So we could say housing model.h5, that's the file format. So we'll put that in here, and then if we refresh in files, you'll see housing model.h5 is here. So you can download this and then you can run this anywhere, or basically if you wanted to pull up on this model, so say you want to make another prediction but you don't want to retrain the model, we'll set old model equal to keras.models.load model, and it's going to be housing model.h5. So we do this, and then it's going to call on this right here. So it's going to load up the same weights, and then you see right here if we redo this code right here, it's going to output the exact same value. So that's how you save models, and then if you want to put this in a website, you could just add this to Flask, add this to a Python file, whatever you want, but that's basically how you save and load models. But yeah guys, that's pretty much it. So we just made our model a lot more accurate in predicting housing prices with square footage. In the next video, we're going to be working with something a little bit more difficult. We are going to be predicting handwritten digits and then assigning them to what the digits actually represent. So we're going to train a model that can see a number and then say what that number is, which is pretty cool. But yeah, guys, that's pretty much it, and I'll see you in the next one. Alright, guys, so at this point in the course, we should already be familiar with how neural networks work and how to implement them in Keras. But today we are going to be working with a slightly more complex neural network, and that is a convolutional neural network. And convolutional neural networks are especially helpful when we're working with any type of image recognition. And this is because, unlike a traditional neural network where it's going to feed the network one pixel at a time, a convolutional neural network is going to feed the neural network in convolutions, which is a chunk of the image. So for instance, a traditional neural network would be one pixel at a time. A convolutional neural network is going to say this part of the image, then this part of the image, then this part of the image. And the idea behind this is that because the neural network is being fed in chunks, it's going to pick up on certain patterns in the data that it can't pick up when it's only being fed through one pixel at a time. So one chunk might have a certain edge or line that's going to help the neural network decide what it is. And so this is why convolutional neural networks are extremely helpful when we're working with image recognition. But that's enough about basic convolutional neural networks. Let's talk a little bit about the data set. So the data set that we are going to be using is called MNIST, and this is a data set so famous that it's already in Keras. So all we have to do is say import Keras, and then MNIST equals keras.datasets.mnist, and our data is in Colab. So that's really cool. Basically what MNIST is it's a collection of handwritten digits and then their corresponding Y value, which is what the digit actually is. So we are going to train a neural network to be able to take an image in and then tell you what number that image is. So without further ado, let's get started. So we already have Keras imported. Next, what we're going to do is we're going to set the X train, the Y train, the X test, and the Y test. So basically, 60,000 images are going to be for the training, and then 10,000 images are going to be what we set our model on, what we test our model on. So in order to do that, all we're going to say is X underscore train, comma, Y underscore train. Then we're going to say comma, X underscore test, comma, Y underscore test. And that is going to be equal to mnist.load data. So this should load MNIST into Colab. We'll give it a shift enter. Alright, it looks like everything's working fine there. Next, what we're going to do is just to sort of show you what the data looks like, I'm going to import matplotlib.pyplot as plt. And then I'm going to print out the first image in our data set. So we'll say plt.imshow x train 0 plt.show, and then I'll also print out to Colab the corresponding Y value with that. So we'll say Y train 0. So we'll print this out, and here you see we have a 28 by 28 image, and you can see it's clearly a handwritten 5, and then its corresponding Y value right here is 5. Alright, so that looks good. Next, what we're going to do is we're going to break down the data so that the neural network can digest it easier. So we are going to take this 28 by 28 image and make it as simple as possible so that the neural network can not waste too much computing power on little things and just focus on trying to identify the image. So this will save us some time and also save us some error. It's going to make our model more accurate. So the first thing that we want to do is we want to reshape all of the images. So we'll just say x underscore train is equal to x underscore train dot reshape. And if we press tab here, we see we need the shape, which is just going to be x underscore train dot shape 0. And then we're going to say 28 by 28 by 1. So 28 being the height of the image, then the width of the image, then 1 being the z value, or the thickness of the image, and because we're only working with two-dimensional images here, we're just going to say it's equal to 1 pixel. Now the cool thing is in Keras you can actually work with three-dimensional images, but we're not going to be doing that today. So, and whenever you're working with one-dimensional images, just remember to keep this at 1. And then let's do the same thing for X test. So I'm going to copy this line here and then paste it here. So X test will also have a different shape. X test that shape. And then finally, let's set the input shape. So this is going to be the shape that we're inputting into the neural network. And if you can guess what this shape is going to be, it is 28 by 28 by 1, which is the size of our image, of course. Finally, what we want to do is we want to normalize the image values. So right now, each pixel is on a value of 0 to 255, with 0 being purple and then 5 being the brightest yellow here. So this is kind of unnecessary for our neural network to be thinking between 0 and 255. Instead, what we're going to have is we're going to have the neural network being imported values from 0 to 1. So we're going to normalize the data set. And this is pretty common within machine learning. And all we have to do for it is just say x underscore train equals x underscore train dot as type. Make sure that it's a float 32. We don't need 64-bit. And then we'll say x underscore train slash equals to 255. And basically what this means is slash equals is the same thing as plus equals, except for you're dividing instead of adding. So all we're doing here is just converting the x train to float 32 and then dividing it by 255 so that every value is out of 1. So we've done that for x train. Now let's do that for x test. So I'll copy these two lines, paste them below, and we'll say x test is equal to x test dot as type float 32 x test slash equals 255. All right, we'll run that cell, and it looks like everything is going good. So next what we're going to do is we are going to convert the y values into ones and zeros, making them categorical variables. So this is called one-hot encoding, and without it, the neural network might categorize numbers based on how they are related numerically rather than how they look. So basically, because we can only have digits from 0 to 9, there is no 0.5, there are no fractions. Because of that, we have categorical variables. So it's either a 4 or a 5. It's either a number between 0 through 9. It can't be anything else. And because of that, what we have to do is we have to one-hot encode our y values. So this might seem a little bit complex the way that I'm saying it, but hopefully when you see it in code, you'll get a better understanding of what I'm talking about. Basically, what I'm going to do to show you how it works is I'm going to print y train 0. So I'm going to print the first y train value. And then I'm going to say y train is equal to keras.utils.to underscore categorical. And then we'll say y train and then 10, because there are 10 possible classes, which are the digits 0 through 9. We'll do the same thing with y test. So I'll just copy this line, paste it here, say y test. Okay, that looks good. And now that we've gone to categorical, now that we've one-hot encoded our y values, I'm going to print y train 0 again. So let's run that. And you see our first y train by default is 5. And now it is this array with a bunch of zeros and 1, 1. So essentially what we did is right here it says 5. What we're saying now is that it's not 0, which is why we have a 0 here. It's not 1, which is why there's a 0. It's not 2. It's not 3. It's not 4. it is 5, so this value is going to be equal to 1 instead of 0, and it's not 6, it's not 7, it's not 8, it's not 9. So when we run the model, what it's going to do is it's going to perform an array, and it's going to say, okay, we are 10% sure it's a 0, we're 0% sure it's a 1, etc., etc. We're 95% sure it's a 5, and then it's going to say, okay, if we're 95% sure it's a 5, and none of these other values are even close to that number, we're going to say that this number is a 5. So that's basically what we want our model to sort of figure out, and that's why we use one-hot encoding. Otherwise, it might think, okay, we think it's maybe a 4, we also think it's maybe a 3, so then we're going to take the average of both of those and say that it's a 3.5. And that's not how we want our model to think. We want our model to think categorically, which is why we use one-hot encoding. Alright, so now it's time to actually build the model, and bear with me because we're going to be working with a lot of new layers that we haven't worked with before, and I'll try my best to explain what each of them does, but if you want to get more in-depth research of what they're actually doing mathematically, I have some links in the description for that. So basically, the first thing that we're going to do is create our model. So we're going to say model is equal to keras.models.sequential. Next, we are going to have our input layer, and our input layer will be a convolutional layer. So we'll say model.add keras.layers.conv2d, because remember we can also do 3D convolutions in Keras, but we're sticking to 2D. conv2d, and then inside of here we'll have 32 neurons. Our kernel size will be equal to 3 by 3, and basically what kernel size is if you remember to the beginning of this video when I was talking about how convolutional neural networks, they take a chunk of the image at a time and feed that into the neural network. Our kernel size is the size of the chunks basically, which is going to be 3 by 3 pixels. And again, you can adjust these values how you want. I got this part of this code off of the Keras website, so this is supposed to be one of the more accurate ways to do this. Next, we're going to set our activation function, which is going to be ReLU. And we are also going to set our input shape equal to input shape, which is the variable that you see we set up here, 28 by 28 by 1. Alright, so that's our input layer, all nice and done for us. Next, what we're going to do is we're going to add another convolutional layer. So we'll say model.add keras.layers.conv2d. This one we'll say has 64 neurons, so twice as many neurons. The kernel size will be the same, which is 3 by 3. And we'll also set the activation equal to ReLU. So ReLU will be our activation function for that. Now what we're going to do is we're going to make a max pooling layer. And to put it simply, what max pooling is going to do is going to take a section of our image, and it's only going to display, it's going to turn 4 pixels, 2 by 2 pixels, into just 1 pixel by taking the max pixel of that image. And you can set it, it doesn't have to be 2 by 2, it can be 3 by 3, but in this example we're going to set it equal to 2 by 2. So basically, because it's setting every 4 pixels to just 1 pixel, we're decreasing our image by a fourth, but we're also still maintaining the features because it's only taking the max value, which theoretically would be the most interesting pixel because it's the pixel that's the most different. So we'll say model.add keras.layers.max pooling 2D, and we'll set the pool size equal to 2 by 2 because we want every 4 pixels to become only 1 pixel. Alright, so that looks good. Next, what we're going to do is we're going to create a dropout layer. And basically what a dropout layer is going to do is, because we have so many neurons, we have 32 neurons in our first layer and 64 in our second, because we have so many, there's a good probability that some of those neurons just aren't going to be helping our model. They're going to take extra computational time, and they can even be hurting our accuracy. And so to prevent that, what we do is we create a dropout layer, which is basically going to randomly select a neuron and then just stop using that neuron and then find out which neurons are actually working the best. So this helps simplify our model a little bit. So we'll say model.add keras.layers.dropout, and we're going to say the probability of a layer getting dropped out at this point is going to be 0.25 or 25%. Next, we're going to flatten the image, and to do that, we're going to say model.add keras.layers.flatten. And if you see right here in our image, we have some pixel values that are kind of greenish or blue instead of just being purple or yellow. And all flattening is going to do is it's going to make this as extreme as possible. So basically either make that value 1 or 0. Or before we ran this cell, it would be 0 or 255. Okay, so now that we have our image flattened with a flattening layer, we are going to add another dense layer just for fun. So we'll say model.add keras.layers.dense. We'll set it with 128 neurons, and the activation will be equal to ReLU. Again, we'll be using rectified linear units. Finally, we're going to add another dropout layer. So model.add keras.layers.dropout, and we'll set that probability equal to 0.5 because 128 neurons is quite a bit, and there's a good probability that a lot of those neurons won't be helping our model. Finally, we are going to add the output layer. So we're going to say model.add keras.layers.dense, and we are going to set the dense layer equal to the number of classes, which is 10, any digit between 0 and 9, and the activation this time is going to be the softmax function. Alright, so let's run that and see how it works. It looks like everything's fine with our model. So finally, it's time to get training. So we're going to say model.compile, and we are going to compile the loss function is going to equal to keras.losses.categorical cross entropy, because again, this is a categorical problem. And the optimizer, instead of using atom, we're going to use another one called adagrad. Optimizer is going to be keras.optimizers.ada delta, and we'll do that just for fun. And then again, the metrics that we are trying to measure for is going to be accuracy. Alright, finally it's time to train our model, so we're going to say model.fit xtrain to ytrain. We'll just set the batch size equal to 128. We'll set the epochs equal to 20, and our validation for this will be equal to validation data for this will be equal to the X test and the Y test. Okay, so I'm going to run that now, and I'm going to speed up the video so that you guys won't have to wait for that, and I'll see you then. Okay, so it looks like our model's done training. It also looks like we should have done early stopping because there isn't that much improvement, especially in the last epochs. But again, on MNIST dataset, you want to make it as accurate as possible because you could be potentially feeding a lot of numbers through it, and you want to make sure that you have as little errors as possible. But I hope you guys enjoyed your break. I walked my dog, ate lunch, had a good time. It took me on the Colab GPU about 30 or 40 minutes for this to train, so that's cool. But now it's time to finally print the accuracy of our model. And it looks like right now it says it's about at 99.2%, which is pretty good. But let's just run it again on the test data. So we're going to print model.evaluate x test y test, and we're going to print that out. It's gonna it's gonna run on all the testing samples, which we have 10,000 of. And you see right here, this first number is the loss, and the second number is the accuracy out of 1. So we see that our total accuracy is 99.2%. So congratulations, guys, you officially created a convolutional neural network in Keras. Thank you so much for watching, and I'll see you in the next one. Alright guys, so at this point in the course we've built a lot of different types of neural networks and machine learning algorithms, but now we are going to build a recurrent neural network, and this recurrent neural network is going to take in text from an author, a very large text file, and then generate its own original text in the style of that author. And the reason why we're using a recurrent neural network is because recurrent neural networks work really well with what we call sequential data. So sequential data is going to be things like music, stock prices, and text. Basically, the idea is that sequential data is when the data point before a data point affects that data point. So what do I mean by this? If you think about in music, if you want to most accurately predict what note is going to come next, you're going to have to look at the previous notes that came before it. And it's the same thing in text. If you want to know what letter is going to come next in a word, you're going to have to look at the letters that came before it and see which letter would form an actual word. So that's the basic idea behind this, and to put it very simply, and obviously I'll have in the link in the description that's going to explain the math behind neural networks. Basically what the recurrent neural network is going to do is it's going to have a data point inputted in, and then it's going to have the next data point inputted into the neural network with the weights of the previous data point. So this is going to allow the neural network to learn based on time sequence data, based on sequential data. So that's just a basic overview. Again, if you want to learn more, there's a link in the description. But for now, we are going to get started actually building our neural network. So the first thing that we're going to do is we're going to import our dependencies. So we're going to import Keras, import numpy as np, and finally we are going to import random. Now we're going to import the data set, and the data set that I have is from Amazon Web Services. It is a collection of the works of German philosopher Nietzsche, and so I'm going to run the recurrent neural network on this data set, and then the recurrent neural network is going to produce fake quotes from the German philosopher Nietzsche. So again, you can do this on whatever you want. If you want to do this on song lyrics, like generate new song lyrics in the style of an artist, I have a file that's on the GitHub. It's called lyricdownloader.py, and basically right here where it says artist name, you input the name of the artist that you want, and it's going to download all of their lyrics from azlyrics.com, which is a very popular site for finding lyrics. But anyways, enough with that. It's time for us to import the data set. So I'm going to import IO, and I'm going to say the path to this data set is equal to keras.utils.data utils.get_file, and then in here the file is going to be Nietzsche.txt, so that's spelled NIETZSCHE.txt. I know it's very difficult to spell. And then the source of this file, or the origin, is going to be equal to https://s3.amazon.aws.com/NIETZSCHE.txt. And then now that we have the path imported, we are going to import the text data set just like if it were on our local machine. We're going to say with io.open path, and we're going to set the encoding equal to UTF-8, so we'll just make it a little bit easier for us. As f, we're going to say the text is going to equal to f.read.lower. And the reason why we're doing lower is we want to set everything in the text to lowercase, so then the neural network doesn't have to learn capitalization rules on top of grammar rules, spelling, and everything else that it needs in order to generate quotes in the style of the German philosopher Nietzsche. And then finally, let's just print the length of the text so that we can kind of see what type of data set we're looking at. So we see right here we have 600,000 characters, which is quite a lot. Again, you want to make sure that your data set is as large as possible, or else your neural network is going to do two things. One, it's just going to output a bunch of garbage because it can't really learn the style. Or two, it's just going to copy verbatim from the data set, and that's not good either because we want to generate original text. And again, that all depends on epochs and all the other training hyperparameters, which we'll talk about a little bit more later. Alright, so now that we have the data set imported, next what we need to do is right now the data set is imported, but everything is in characters. We need to take these characters and we need to turn them into numbers. So if you're already working with stock price data, then you don't have to do this because your data is already in numbers. But basically we have to convert every single character into a number, so then the neural network is actually predicting what number comes next. Anyways, and we're going to do one-hot encoding sort of as well, because obviously there's no mathematical relation between like A and B and A and C, so we need to make sure that those are categorical variables. So bear with me, this is going to be kind of long and complicated, but I promise it'll make sense later. So we're going to say chars are equal to sorted list set text, and then we're just going to print the chars, print the length of the chars. Alright, so you see we have 57 different characters, which is pretty good. Next, what we need to do is we need to assign those 57 characters to numbers, and then we need to go through the entire data set and convert that all into numbers. So I'm going to say char underscore indices is equal to, we're going to create a dictionary. That dictionary is going to have the dimensions of c, comma I, for I, comma c in, and we're going to say enumerate chars. There we go. And we're going to do the same thing, but we're going to say indices underscore char is equal to dict, and it's going to be I, comma c for I, comma in c for I, comma c in enumerate. Let me spell that right. Enumerate chars. Alright, so we'll run that. Okay, it looks like everything ran smoothly with that. Next, what we're going to do is we are going to create lists, and that's going to have all of our data in it. So we've sort of assigned each character to a number. Now what we need to do is go through the entire data set and convert everything. So first we're going to create an empty array called sentences. So say sentences equals to empty square brackets. And we're also going to create an empty array called next underscore chars. After that, what we're going to do is we're going to create a for loop. So we're going to say for I in range 0, comma length of text minus 40, comma 3 minus 40, comma 3. And basically what this is going to do is it's going to go through the corpus of our data set, and it's going to chunk it up, and then it's going to go through and it's going to enumerate everything. So this might not fully make sense, and a lot of these numbers you can play around with. Just this makes sure that everything goes through, gets enumerated, gets turned into a number instead of a letter, and it also doesn't overload the RAM or anything like that. So inside this for loop, we're going to say sentences dot append text, open square brackets, I colon I plus 40. So I'm using the number 40 because that's just going to represent a word, even though obviously most words are well below 40 characters. And we're going to say next underscore chars dot append, and we're going to append text and we're going to say I plus 40. Alright, so now that that all looks good, we're going to create our x and y variables. So x is going to be set to a numpy 0 array, so np dot zeros. And if we look here, it says the first thing we need is the shape. So I'm going to set the shape equal to the length of sentences, 40, and then the length of the characters. And then we're going to say the data type, or the D type, is going to equal to np.bool for Boolean, because it's going to be a Boolean type. And the y variable is going to be the same thing as the x variable, so np.zeros, except for in the shape we aren't going to have the number 40. So it's going to be np.zeros, the length of sentences, comma, the length of chars, and the data type will also be D type equal to np.bool. Alright, so we got our x and y variables set up. Finally, we're going to run two last for loops, nested for loops that is. So for I, comma, sentence in enumerate sentences, we're going to say for t, comma, char in enumerate sentence x square brackets I, comma, t, and again the t and the I can be set to whatever you want to. I just find that using one letter variables when we're talking about loops works a lot faster. Char underscore indices square brackets char, and we're going to set that equal to 1, and then outside of this for loop we're going to say y I, comma, char underscore indices square brackets next underscore chars square brackets I is also equal to 1. So let's run that, and it's going through the corpus of the text, and now it looks like everything is converted from ABCD to 1, 2, 3, 4, which is a good sign. So you can see all of this code right here was just working with the data set. Now it's time to actually create our neural network. So by now you should already know the deal. We're going to say model is equal to keras.models.sequential. Next, what we're going to do is we're going to add our first layer. So we're going to say model.add keras.layers.lstm. And basically what LSTM stands for is long short-term memory, and this is a slight modification of the RNN model right here that we see in this picture, where it's going to make sure that the neural network remembers certain things but also forgets other things. That's what the long short-term memory stands for. Because our text is so long, you gotta make sure that the model remembers certain things about the text but then forgets other more minor features. So the math behind this is kind of complex. I'll post links in the description down below for you to read if you want more, but for now we are just going to create the model and not go in too much about how it works, just sort of give you the basics. So that's going to have 128 neurons, and we're going to set the input underscore shape equal to 40, which is the number that we've been using throughout this whole file. 40, and the length of chars. And then next what we're going to do is we're going to add another layer, model.add, and this is going to be a dense layer, so we're going to say keras.layers.dense, and we're going to set the number of neurons equal to the length of chars. And just a good rule of thumb, when you're adjusting hyperparameters and you don't really know how many neurons you want in a specific layer, a good rule of thumb is just to go for the amount of attributes that you have. So in this case, the length of characters. In the housing prices example, the number of attributes that we had, stuff like that. and we're going to set the activation function. Let's go with a softmax, which is an interesting name to say the least. Next, what we're going to do is we're going to compile the model. So we're going to say model.compile. The loss function is going to equal to categorical underscore cross entropy, and the optimizer is going to be equal to keras.optimizers.rms prop, and we're going to set the learning rate to something small. Let's go with 0.01. I don't know why RMS prop works really well in this model, but I heard it does, so we're just going to go with that. And of course we want the learning rate to be small because we have a relatively large data set and we're going to be going through a lot of epochs, so we don't want the model to make too many assumptions too quickly. Alright, so let's run that. Okay, looks like our model's all nice and compiled, so that's good. Next, what we're going to do is we are going to create a function that's going to give us some sample text. So we're going to say def sample, and the parameters are going to take in is preds for prediction, and the temperature is going to equal to 1.0. And basically what temperature is how much randomness is going to be in the model. So I use 1.0 because I feel like that's not so much randomness where it's going to input just completely garbage text, just gibberish, and not too much where it's just going to be straight up copying from the training set. So we'll do that, and we'll say preds is going to be equal to np.asArray preds.asType, and we want float 64. Okay, that looks good. Next we're going to say preds is equal to the np.log of preds divided by temperature. So this is sort of how temperature works. It's going to simplify the model a bit more. So you see when the temperature is 0.1, the preds is going to equal to np.log preds over temperature, which is 1, which means that it's just equal to np.log of preds. And then we're going to say that exponent of preds is equal to np.exp preds, and we're going to set preds equal to, once again, to the exp underscore preds divided by np.sum exp underscore preds. Finally, we're going to set probos equal to np.random.multinomial 1, preds, 1 for our dimensions. And then we're going to say return np.argmax probos. So that's everything that we need for our neural network to start displaying the results of its findings. Next, what we're going to do is we're going to train the model. So first thing we're going to say is we're going to say model.fit, and we're going to fit the x to the y. We're going to make the batch underscore size equal to 18, and the epochs I'm going to set to equal 1, but what you're going to want to do is have a much higher epoch count. It's just because this model takes a really long time to train, so for time purposes I'm just going to set it to 1 epoch. Next, what we're going to do is we're going to declare a variable called start underscore index, and that's going to equal to random.randint 0, the length of the text minus 40 minus 1. Alright, now that we have the start index, we're going to say for diversity in, and then we're going to open up an array in here, and we're going to say 0.2, 0.5, 1.0, 1.2. So for that list, diversity in that list, we're going to say generated, and this is going to be where we're going to store our generated text. Generated equals an empty string, and the sentence is going to equal to text start underscore index start underscore index plus 40. So basically the start index variable right up here, what it's doing is it's going through the text and selecting a random part. So the sentence is going to equal one 40 character chunk randomly in the text, and then the model is going to try to predict what comes next after that, and that's going to be our generated text, which we're going to store in the empty string variable called generated. And then we're going to say generated plus equals sentence. Alright, now we're going to say for I in range 400, and this is going to depend on how large you want your output text to be. Actually, I'll make it 600, so we'll have like about a 600 character long sample passage that the model generated. We'll say x underscore pred equals, and we'll do a numpy array with 0, so np dot zeros 140 and the length of chars. Next, we're going to say for t comma char in enumerate sentence x underscore pred open square brackets 0 comma t comma char underscore indices char, and we're going to set that equal to 1. So this should look familiar to what we did up here in this part of the code, and that's because we're essentially doing the same thing with outputting and training the model as we did with converting it all to numbers. So that equals 1. Next, outside of the first for loop, we're going to say preds is equal to model dot predict, and we're going to do the x underscore pred and the y, sorry, not the y, we're going to predict the x underscore pred with a verbose equal to 0, and verbose, this is just basically just a variable of how much the model is going to repeat itself, stuff like that, and we're going to say 0 in the square brackets here. Now we're going to create a variable called next underscore index, and that's going to equal to sample, we're going to say preds and diversity, and then we're going to say next underscore char is going to be equal to indices underscore char next underscore index, and then the generated variable is going to plus equal the next underscore char that the model predicts, and the sentence is going to equal to sentence 1 colon plus the next underscore char. And then finally, we're going to take this generated and we're going to write it to a file. So we're going to say outside of this for loop here with open, and we'll name the file that we're going to store our example text in as example.txt comma w for write, because we're writing to the file, as f dot write generated. So basically all this is doing right here is this is making sure that the generated string that we have of example text in the style of Friedrich Nietzsche is being written to a file called example.txt, which we will be able to see right here. Alright, so everything looks good. Now let's run our model. Okay, so it looks like our model is done training. We can see I only went through one epoch. Let's see how much it learned in one epoch. So I'm going to refresh, and we see right here we have example.txt. I'm going to open it up, And you can see already some of these look like actual words. So we have colors, with, the, and obviously this doesn't make any sense whatsoever, but in just one epoch, in just about 7 minutes on Colab, the model went from knowing absolutely nothing at all to sort of learning how to spell a little bit. So that's really cool, guys. Thank you guys so much for watching, and I'll see you in the next one. Sweet.
Thank you guys so much for making it to the end of this video. As always, if you enjoyed it, make sure to hit that like button. Also, if you have any questions, comments, or concerns about what we did in this video, please leave them down below. Now, if I could have just one more minute of your time, I would like to tell you about a service that I've been using for over a year now called Scribd. Now, just as a side note, Scribd did not sponsor me to make this video. I just wanted to tell you about it. Put simply, Scribd is a lot like Audible, except for instead of being $15 a month, it's only $9, and instead of only having 2 audiobooks per month, you get an unlimited access to a plethora of audiobooks, ebooks, documents, and even sheet music and magazines. So for me, this was obviously a no-brainer, and right now, if you use the link in the description, you get 60 days free of Scribd, and I get 1 month if you sign up using my link. So that's why Scribd didn't officially sponsor this video. I'm just telling you about it so that I can get some free months and I can continue learning, and you can also continue learning with your 60-day free trial. So thank you guys so much for making it to the end of this video, and I'll see you in the next one. Peace.